Hey everybody, welcome to another exciting digital design class. In our last class, we introduced a topic called canonical sum of products and canonical product of sums. And we had an idea that if you could have a function of x, y, and z, that every product term would appear with both. Oh, could you mute, please?
Starting to look like me, and I don't like it.
Thank you. Every product term would be included. So if we said something like x, y, z, or x prime, y, z, or x prime, y prime, z, we knew we were in a canonical product of sums form because the x, y, and z appeared in every single product term, either in its inverted or uninverted form. Moreover, if we got the binary encoding for the term, we would write it out as 1, 1, 1 if nothing was inverted. We'd write it out as 0, 1, 1 if we saw something like x was inverted, and 0, 0, 1 if we saw that x and y were inverted. And so we would write this out as the M7 term, and then the M3 term, and then the M1 term. And by doing so, we could write out a truth table in x, y, and z. And we could number our truth table. And so by inspection, we're able to fill out M7 as a 1. That's the seventh element. I'll make some lines in here so that we can keep things straight. M3 is a 1, so we put a 1 under the 3 column. M1 is a 1, so we put a 1 in the 1 column, and everybody else gets 0. And so now we see a direct mapping between the product term and the truth table. Does everybody sort of see that? So if we write M sub I in here, it's M sub 0, M sub 1, M sub 2, M sub 3, M sub 4, M sub 5, M sub 6, and then M sub 7. And that's how you get a truth table to map into a canonical form. Moreover, we have a shorthand notation that says F is equal to, and then we use sigma, M, and then we just write out the index terms, typically in ascending order, 1, 3, and 7. And so that is a shorthand for the longhand M1, M3, M7, which is actually another shorthand for the canonical form with every term written out in every product term. Every variable is in every product term. So that's the bird's eye lowdown on the canonical sum of products caper. What do you think of that? Anybody confused by canonical sum of products?
Yeah, I have a quick question.
Sure.
It just slipped my mind for some reason. Can you walk me through how you said M7 is equal to 1, M3 is 1, and M1 is 1?
So M7 has the binary equivalent of 1, 1, 1. And M3 has the binary equivalent of 0, 1, 1.
Oh, okay, I got you.
So we're taking the radix 10 number in the index M1 and representing it in binary. And we're drawing a correspondence between the binary representation and whether or not the variable in the product term is inverted. If it's a 0, the product term variable is inverted. If it's a 1, the product term variable is not inverted. Is it making sense? Yeah, it's good. It's good.
Yeah.
So at some level, one could make a compelling argument that this is not a minimal form. Not generally. It might be, but it's not generally minimal. Not generally. So now we can keep in mind M1, M3, and M7 are all part of what we will call members of the on set. But it should be possible for us to find a different function, which we will call f prime. And now with f prime, we can find the complement of the set. And that is going to be m of, and now we use all the members of the offset. So that's m0, 2, 4, 5, and 6. And so now we have f prime, you see. And we were able to obtain f prime simply by using the members of the offset. Is it making sense? People okay with this? Any questions? Let's try.
I had a quick question.
Yeah,
Sorry,
sure.
Professor. So in the initial function that we wrote, how come there's no z prime? Like, didn't you say that for the canonical sum of products that there has to be a representation of each type, or is that not necessarily true?
Yeah, you don't need to have every complement and every non-complement in every expression, but you do need to have the variable x, y, and z in every product term, either in its inverted or non-inverted form.
Okay, thank you.
Yeah. Any other questions? Let's try another example. This one we'll make a little bit smaller. We'll start with the truth table now. We'll number the truth table m sub I, and then we'll find a function. Let's write f in canonical sum of products shorthand notation. So that's going to be m1 and m2. Now let's write it out in longer hand, m1 plus m2. Now let's write out the binary. And now let's write it out as a, well, let's not use a because we're in x and y, so we'll use x. X prime y, or x y prime. Does everybody kind of see how I was able to get x prime y and x y prime? Any questions so far? So then, if that's true, what does f prime equal in canonical sum of products shorthand notation? You tell me. Andrew, you want to take a stab at it?
So we said that was 1 and 2, so it would just be 0 and 3.
Exactly right. That's exactly right. Does everybody kind of see why that's true? So good. So then what we'll do is we'll write this out in slightly longhand notation. M0 plus M3 is equal to F prime. And then what we'll do is we'll write it out in binary, and we'll write out 0, 0, 1, 1, which basically writes out to X, Y, both prime, or X, Y, neither of them prime. And so these are the product terms needed to reconstitute the truth table for F prime, the complement. But somebody said something or other about F. I can get F and set it equal to X prime, Y prime, or XY inverted. That is to say, I can invert both sides of the equal sign. And if I were to do so, I could imply that maybe I can write f in a different form. And that form will have x prime, y prime, quantity primed, plus gets turned to times xy quantity primed. And now with De Morgan's theorem, I can write x or y times x or y prime. And this is a canonical product of sums. And so we can get the canonical product of sums by starting with a canonical sum of products for f prime, writing it out using De Morgan's theorem, and then proceeding to show the canonical product of sums algebraically. Now who's confused? I don't believe you. Somebody's confused.
I'm confused.
Oh, good. Okay. Now, where did I lose you?
When you rewrote it again, like f
Right here.
equals x prime, y prime, and then all that prime, and then x, y. Yeah, right there.
This part? Okay. Let's do the following. Let's take this right in here and rewrite it up here using De Morgan's theorem. So that's going to be x prime, y prime. The prime propagates to the inside. The plus gets turned to times. And the xy gets written in here. So using De Morgan's theorem, plus gets turned to times, and the inversion gets propagated to the inside of the parenthesis. I have to apply De Morgan's theorem again, this is the second time in a row. And now I have x prime prime or y prime prime times x prime or y prime. But x prime prime is x. And so I can write x or y times x or y, both primed. Now, how did that grab you?
Yeah, that made more sense.
Made more sense. All right, so let's take a look at this expression right in through here. I'd like to know if I can simplify that expression. So what I'll do is I'll erase some stuff over here, and then I'm going to rewrite this expression. And then I'm going to cross multiply. So x times x prime is 0. X times y prime is xy prime. X prime times y is equal to x prime y. Y times y prime is 0. So f is equal to this, which says that m1 or m2, well, let's see now. No, that's m2 versus m1. m2, do it again. m2 or m1 equals f. And sure enough, that's what we got, m2 and m1. So that's the proof that they're equivalent algebraically, but this is how you obtain the canonical product of sums from a canonical sum of products and De Morgan's theorem. Now who's confused? Nobody? That's good. That's good. Let's try another example. f of x comma y is equal to m0 or m1. Find f prime of x comma y in canonical sum of products shorthand notation. What are the indices? Mariana, you want to take a stab at it?
Would it be M of 2 and M of 3?
Sounds good to me. So in other words, with 2 bits, you get to go 0, 1, 2, 3. And the first 2 are equal to 1. And the last 2 are equal to 0. And therefore, 2 and 3 are members of the offset, and that will be equal to f prime. Does everybody kind of see what happened there? So let's take a look at this expression, m2 plus m3. Let's write it in binary. And now let's write it in algebra. So it's clear on a couple of points. First, we're easily able to find the complement using canonical product of sums shorthand notation. We're also able to write it out in longhand. And finally, it's clear from this expression, it is not a minimal form, because we could always factor x out and write x prime or y, and x prime or y cancels itself out to 1. And so then we have it equal to x. So it's not a minimal form by any means. It's a canonical form. And normally canonical forms are not minimal, in general anyway. What do you think of that?
Professor, could you just go back to the truth table for a second, and where in the column for the function you went 1 1 0 0? Can you just go over that one more time, please?
Sure. So on this page, we have a truth table where we're counting in binary. And so we go 0 0 0 1 1 0 1 1. Then we say, let's assign values to f. And the first 2 rows assign value of 1 to f. So that says that we're going to have f equal to m0 and m1. And that's fine. But then somebody says, well, let's go find f prime. So for f prime, I have to find the members of the onset, and they have the canonical shorthand notation 2 comma 3, because that's where the zeros are. Let me change colors here, make it nice and green. There. So you can see the zeros are on rows 2 and 3, and that corresponds to m2 plus m3. So when you go in over here and you look at the canonical sum of products in shorthand notation for f prime, you see 2 comma 3. Then we proceed to write out m2 and m3 here. And then we write out the binary representation of the radix 10 indices. And that gives rise to the algebraic expression, which has a common term x that we can factor out. Y or y prime must be equal to 0. No, must be equal to 1, because if y is equal to 0, then y is 1. If y is equal to 1, if y prime is equal to 1, then y is equal to 0. And 0 or 1 must be equal to 1. And x times 1 is equal to x. And so we can obtain a simplification showing the point, which is that canonical sums of products are typically speaking not minimal forms. What do you think of that?
Thank you. So I guess, so we're given what the truth table would say
Yeah.
for the function. Okay, I guess that's what I was confused about. I wasn't sure if that was something we
Yeah, I was,
derived.
you can start anywhere, actually. You could be given the shorthand notation, you could be given the truth table, you could be given an algebraic expression. You could be given an algebraic expression that's not in a canonical form, and then you might be asked to derive the truth table, or even better, let's start with a circuit. That's good. We haven't done that before. Given the following circuit, how do we find the algebraic representation for this circuit? Well, let's break it down into smaller chunks. What comes out of the NAND gate is going to be x times y inverted. What comes over here out of the NAND gate is going to be x prime y prime inverted. So now that means that f is going to be equal to xy prime on the input times x prime y prime also on the input, multiplied together, quantity inverted. Now, using De Morgan's theorem, I can write that xy prime prime plus x prime y prime 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 must be equal to f. And the prime primes cancel each other out because two wrongs made a right, and two rights made an airplane. So now we can write x prime y prime, and that's equal to f. Now, what does the canonical sum of product shorthand notation say? This is going to be 1, 1. That'll be 0, 0. And that must be equal to m3 plus m0. So in shorthand notation, we write 0, comma 3. And if we want the truth table, we can write out the following. And there's that. Okay, now who's confused? So we can start with a circuit. We can obtain an algebraic expression. We can simplify using regular theorems. And then we used a mapping between the variables and their binary representations to obtain the indices for the shorthand notation. Once we had shorthand notation, it was relatively simple to, I think I made a mistake here. It was M0. Yeah, M0 and M3. No, I got it right. I got it right. I was going to say. That's fine. So M0 and M3 are directly corresponding to these indices in here. How's that? Is everybody kind of on the same page now? Are we all understanding this? Who's confused? Be honest. Anybody got confused by this?
So, sorry, just to clarify from before, kind of similar to the question I asked about the truth table. So the 1001, because we wrote the truth table after we figured out that it was M0 and M3. So just, and the 1 is because that's when, oh, okay, wait, actually, I get it now. Just talking that out there.
We were
I figured that out.
given a circuit and we were asked to do the analysis. So the problem was, given the following circuit, find the truth table. In order for us to do that, we had to write out the algebra, right? Simplify, use De Morgan's theorem, and then obtain the canonical sum of products. And finally, once we had that, we were able to map the canonical sum of products into a truth table. And now that's what we wanted to find. This is a process called reverse engineering. And in reverse engineering, you're given a circuit and then you're asked to describe its behavior at a relatively abstract level. Once you have an abstract version of the circuit, right, you can change how you implement the circuit. For example, you could use AND gates and OR gates, or you could use just NOR gates. So in effect, you can change the circuit around after you reverse engineer it. Kaylee, did I answer your question?
Yeah, I just had a question and how you knew that, like for the given, will we be given like XY inverted? Like, is that what the
Well,
circuit
yeah,
was?
you have to start with something. You could be starting with canonical sum of products shorthand notation. You could start with a circuit. You could start with a truth table. It's all equivalent. Let's try another example, only this time I'm going to start with a canonical sum of products and you're going to design the circuit.
Professor,
Yes.
just before you go on, I just want to clarify something. If you were to move back, X's and Y's just as is are considered to be ones, right? And then X prime, Y prime are considered to be zeros. The primes are zeros and the
Yep.
X and Y. Okay, thank you.
Yeah, you could do it with A and B. You could do it with W and Z. You could do it with that, whatever you like. Any variables, doesn't matter. We'll do another one. Let's do F of, we'll change the variables, A and B and C. And we'll set it equal to canonical sum of products shorthand notation 2, 3, 7. 2, 3, 7. Find, let's say, a circuit that implements that. Implements F. So first thing you might like to do is say, well, it's M2 plus M3 plus M7 that corresponds to 0, 1, 0, 0, 1, 1, 1, 1, 1, which corresponds to A, B, C prime prime, or A, B, C prime, or A, B, C. And now it should be possible for us to find a circuit that could implement this with 3 levels of logic, the inversions needed and gates for each one of A, B, and C. What else? Well, let's assume for the moment that we want to simplify. A prime times B times, well, let's see now. C or C prime is equal to ABC. Oops, sorry, plus ABC is equal to F. So this part goes to 0, or goes to 1 actually. And so now I have A prime B or ABC. So I was able to come up with a little bit of a simplification. We got rid of one of the terms. Let's write out the truth table. A, B, C. And so we know it's going to be M2, M3, and M7. And now I am thinking that's probably all the simplifications we can get right in through here, at least with the algebra we know now. So we'll write it out. AB prime goes into an AND gate. ABC goes into an AND gate. And the whole thing goes into an OR gate. And there's my implementation. So I can start with a canonical sum of products. Do some rudimentary simplifications with Boolean algebraic manipulation. And then take the result and directly map into a circuit. What do you think of that?
Professor, I have a question.
Yes.
So I know for this problem, we knew which values of f were going to be 1 in the truth table, but if we're not given which values, how do you determine which ones are 1 and which ones are 0?
If you don't have a truth table and you don't have a circuit, what do you have? You have to be given something. So you're either given a circuit, or you're given the shorthand notation, or you're given the truth table. So we've got to start somewhere.
Okay, so we're given something, and based off that, we can form our truth table.
Exactly.
Okay.
You could be given a truth table, you might have to find a circuit diagram. You could be given a circuit diagram, you can get the truth table. You can go back and forth. You do need something. You got to start somewhere. Let's try some homework examples, shall we? Now, in our last exciting digital design class, I think we were doing homework 3. Does anybody remember what problem we left at?
I know we did
think it was
question
20.
19.
Sorry, say that again, please.
know
I
we did
see
question
21 in my
19.
notes.
21? Okay. So if we did 21, why don't we look at 23? So let's do 23. So problem 23 says, in sum of products form, only one of the midterms must be true for the expression to be true. So let's look at that. Suppose I said A, B, or A prime B. And I say, well, this one is true. Well, in that case, F is equal to 1. Because if you OR with anything that's 1, the answer will be 1. Why is that? Well, let's take a look at the truth table. Anything is 1, then the output is going to be 1. That's how truth tables work. So the answer to that question must be true. The sum of products form requires only one midterm to be true for the expression to be true. This is different from product of sums form. If one parenthesis group term is true, it's not enough. Everybody has to be true. So the max terms, and each one of these is called a max term, the max term for each element must be true. Or you could say all the max terms must be true for the expression to be true. And that's question 24. What do you think of that? Right? If this were a 0, everything would be 0 because you'd be multiplying by 0. Question 27. What do we call the operation between the parentheses for the max term? And that operation is product. It's an AND operation between the max terms. So AND has maximum satisfiability because the output will be true if and only if the max terms, all the max terms give true. That is to say they're all 1. Let's take a look and see if there are any other questions here that look hard. Anybody have any specific questions they want me to cover?
It's Professor, sorry, I kind of missed. What did you say for 27?
Oh, 27 says that the product of max terms is the product of and the product of sums, and well, it is the product of sums, and so there is an AND operation between the max terms. So AND has maximum satisfiability because the output will be true if and only if all the max terms are true. So in other words, if F is equal to 1, it must be the case that A prime plus B is equal to 1 and A plus B are equal to 1. So that has to be equal to 1. And then this has to be equal to 1. Because if any of them were equal to 0, you'd be multiplying by 0, in which case the output would be 0. What do you think of that? Does it make sense?
Yep, thank you.
All right. Let me see if there's any other questions here we should be covering. Okay, I got a good one for you. Suppose I said F is equal to canonical sum of products 1, 3. Find F in canonical product of sums shorthand notation. SHN stands for shorthand notation. Shorthand notation. So let's take a look and see how we could do that. A couple of ways. One thing I could do is I could try and find F prime. At 0 and 2. Then I could write it out as M0 or M2, which I could then write out as oops. Yeah. And now I can write out F as being equal to and that will give me a canonical product of sums. So that's a way in which we can take a canonical sum of products and turn it into a canonical product of sums. But one other way we can do it is we can write out that the canonical product of sums has a shorthand notation. And that is equal to the pi product, because these are product, basically multiplied together, instead of the sigma where these terms are being added together. And in the pi product, we use capital M because this is max terms. And in those max terms, we write out the complement of the set of terms, that is those elements which are in the, I'll say offset. So what we'll do is we'll write out 0, 2, which is essentially just like what we've written in here with a difference. And difference is the max terms use x uninverted to show this is supposed to be 0, 0, and this is supposed to be 1, 0. So when we look at the book, and this is kind of why I don't like to do it this way, but if you do it with the book's approach, what you do is you interchange the operation of sigma and pi, that is sigma is adding and pi is doing the product, and then you write the indices of the terms that are not presented in the given equation. So if we are looking at canonical forms in 2.2.2, conversion between forms, what we'll see is figure 2.17, page 58. And what he's saying is that M0, capital M0, is equal to A or B or C. In comparison, little m0, I guess to denote that it's little, I'll put a little underline under it. Little m0 must be equal to A, B, C, all prime. And so that kind of makes up the difference. Little m is going to be the min term. Big M is the max term. And so when you're reading the book, you'll see how you can convert directly from canonical sum of products to canonical product of sums simply by changing sigma to pi, little m to big M, and finding the complement of the indices. And so that's what has happened here. We went from little m into big M, we went from sigma to pi, and we formed the complement of the indices. So that sounds easy enough. The real mind-bending part is the fact that we have to complement all the variables and change the times to plus. In effect, it's like applying De Morgan's theorem, which is exactly what we do when we want to change from a canonical sum of products to a canonical product of sums. We change times to plus, plus to times, and we invert the literals. So that is De Morgan's theorem. So in a sense, one could say that M, capital M0 is equal to M0 prime. And that's why you get the literals inverted when you look at the table in figure 2.17. Not to put too fine a point on it, we can write out table 1.7 here. I'll just do the first two variables. All right. And then what we'll do is write out the max terms. Capital M0, capital M1, capital M2, capital M3, and this is going to be A or B, A or B, A or B, A or B, and the inversions will be whenever you see a 1, that's when the variable is inverted, and otherwise it's left alone. So now, if you wanted to go back, can I go back? Can't go back? I just want to go back. Oh, I guess you can't go back. That's weird. Okay. Wait a minute. I have to learn how to use this blackboard. Somewhere in here, there's an eraser. Okay. Yeah, I'm not quite sure how to go back with the whiteboard in Blackboard. But there's a compelling argument that if you write in canonical sum of products form or canonical product of sums form, whichever you like, capital M pi product 1, 2, I can directly map to zero, 3. There. So that's actually a good time for me to suggest that you guys read the book. This is we're on page 56 through 59 with examples on 60 and 61. So you're really where we're at is 56 through 61. Any questions? Shall we try another example? Let's do a homework question. Question 30. So what we'll say is we got a function in canonical sum of products shorthand notation. Zero, 2, 3, 5, and 7. So given the canonical sum of products form, find the canonical product of sums. All right, why don't you guys work on that? You can use shorthand notation, which is a shortcut, actually. Makes it easy. Abraham, you want to give this a try? How about Akul? Akul, you want to give it a go? I'm starting on the A's.
Yeah, 146. So like pi m of 146.
That's exactly right. Capital M, 146. Any questions about how I got that? Or Anybody got that? Is it clear? So let's, now that we have this, let's write out the binary. Okay. So normally we'd write 0, 0, 1, 1, 0, 0, 1, 1, 1. Sorry, 1, 1, 0. But because we're dealing with a product of sums, we use 1, 1, 0. We complement everything, 0, 1, 1, 0, 0, 1. And so now we can write A or B or C prime times A prime or C, sorry, or B, or B or C times A prime or B prime or C. What do you think of that? So now we've got the canonical product of sums in longhand notation, starting from canonical sum of products in shorthand notation. We map directly into canonical product of sums in shorthand notation, and then proceed to write it in binary, rewrite it as a complement, and then write it out as canonical product of sums in longhand notation. So to change the operational function from sum to pi product, we went from sigma to pi. Right, let's try and change colors again. Went from sigma to pi. Right, that was part of the procedure. We wrote the missing indices of the terms 1, 4, and 6. So we got the next step in the procedure is write the missing indices. That's the complement of the set. And then you can write it out directly in longhand notation once you have your indices.
Can you
Professor, I
explain
just have
how
a
you
quick-
went from, oh, sorry.
I just have a quick question. We could do it the
Sure.
other way though, without changing the sigma, right?
Yeah, it is possible to write it all out in a truth table and then find the complement, or you could just find the complement directly, f prime. If you did it that way, right, you could write f prime equals in shorthand notation 1, 4, 6. That's legit. And then you have A, B, C with A, B, C with A, B, C. And then F will be equal to all of the above inverted. And then you can use De Morgan's theorem and you'll get A or B or C prime times A prime or B or C times A prime or B prime or C, which looks like that. So you can use either technique. I like this one better because it doesn't require that you remember how to map from the shorthand notation into the longhand notation. You just use the De Morgan's theorem. That's why I like it better. Kaylee, did I have a question from you?
Yeah, my question was, how did you get from binary to the complement? Is that just f prime or the inverse?
Yeah, so if you look at A, B, C, prime, prime, 1, right? Then form its complement, what you're getting is A or B or C prime, which is what this corresponds to right there. So you're really just using a form of De Morgan's theorem when you proceed to do that. You're changing the signs of the literals and you're changing the times to plus.
Okay, thank you.
Sure thing. Other questions? Canonical forms. Do people get confused by the term canonical? No? Okay.
Yes.
Yes. Okay. So where does the term canonical come from? Any ideas?
The church.
Yes, right. The canons of the church. So it's a regularized expression that's designed to make it so that once you have it in this algebraic form, it's going to look the same as everybody else's form. So in other words, canonical forms are not necessarily simplified, but they are in some sense in a normal form. So that is a, sometimes they call it a conjunctive normal form or a disjunctive normal form in reference to conjunction, which would be and disjunction, which would be or. So if you were in a philosophy class, instead of calling it a canonical form, they'd be calling it a normal form. And instead of a canonical sum of products, it would be a conjunctive normal form. And instead of a canonical product of sums, it would be a disjunctive normal form. So in some sense, they're synonyms. Conjunctive and product versus disjunctive and or. It's just two words, two ways to say the same thing. I think conjunctive and disjunctive sound rather fancy. So leave it to the academics to come up with fancy names for simple ideas. It's just and, right? That's what they do because they just like fancy names. So you'll see canonical sum of products directly maps into conjunctive normal form. And canonical product of sums directly maps into disjunctive normal form. And this is from the philosophy department. And this is from the computer engineering department. And they're basically talking about the same things. Just that they have a different notation and a different name. But they both have De Morgan's theorem. So there are certain things that don't change. I wonder if they do that just to confuse you. But there it is. Every discipline has its own nomenclature. It's quite typical. And if you went into the field of medicine, you'd find tons of nomenclature. And perhaps medicines with impossible to pronounce names. Let's do another example. F of A, B, C equals sigma M 0, 1, 2. Find the canonical product of sums. Someone want to take a stab at that one?
Would it be F equals theta capital M.
And what
Uh,
indices?
3, 4, and 5.
Well, we've got 3 bits. And if you have 3 bits, how high can you count?
Oh, 6,
And
7.
7. Yes. So in other words, if we did something like this, sorry, I got to turn this off. Sorry about that. So if you do something like this, you've got 2 to the 3, which equals 8 different possible places, which takes you from 0 through 7. And that'll give you sorry, I got to turn that off. Give you 8 different symbols. So when you're looking at the set 0 through 7, and you see members of the onset are 0, 1, and 2, then the complement of that set includes 3, 4, 5, 6, and 7. And so that's how you find the canonical form for the product of sums, canonical product of sums. You're finding the complement of the set. And I'd write it out, but it's a little bit long. Not impossibly long, but just not convenient. And how would we write out f prime in canonical sum of products form?
It'd be 3, 4, 5, 6, 7 again.
Exactly, same thing. Oops. Any questions about that? So it sounds like we're getting there. Maybe the thing to do is to start off on homework 4 a little bit and see if we can make some headway with that. What I'd like to do is change gears a little bit. Course content. I'm in Blackboard now, so forgive me while I mutter to myself. Edit. I'm going to take a look at homework 4 to go ahead a little bit. All righty. So let's take a look at what's known as a K-map. K-map is named after Maurice Carnot. Maurice Carnot came up with this idea after looking at a paper by a guy named Vetch. I uploaded the paper to the background information folder, and that's from 1952. And he created what's called a Vetch chart, which was a rediscovery, interestingly enough, of a logic diagram from 1881 by a guy named Marquand. I often wondered, how did Maurice Carnot come up with this K-map idea? The answer is he just built on Vetch. And I thought, well, that means Vetch was the genius. How did Vetch come up with the idea? Well, he came up with it by looking at the work of a logician from the Victorian era. And if you think about it, this guy must have been a contemporary of George Boole. So apparently they were doing a lot of good work in logic back in the Victorian era. And in fact, if we think about it, 150 years ago, in 1871, Babbage had passed away, and he had just finished his magnum opus differential analyzer, which was reconstructed in the Google Computer History Museum as a mechanical computer, and also reconstructed in the London Science Museum which I visited about a year and a half ago and actually got to see the difference analyzer. So it's a full-blown calculator made with nothing more than machine parts, no electronics, completely mechanical. And kind of interesting because it was doing logarithmic tables. So here we are 150 years later, and we're getting Raspberry Pis for $35 and plunking them down on our desks. Interestingly enough, people are saying the next generation will be quantum computers, but people wondered, do quantum computers really work? And the answer is yes, they do. But do they scale is the real question. And some people say you'll need 1 million qubits in order to make a quantum computer. And right now we have like 100. So it might take 10 or more years before we can get down to 1 million qubits, and then maybe we can solve a real problem. Maybe. So might take a while. It took 150 years from Babbage. So hopefully we won't have to wait that long for quantum computers, but who knows? Who knows? So here comes Maurice Carnot, and he's coming up with this new technique for doing what's called Boolean algebraic minimization. And so what we'll do is we'll start off with a thing called a K-map, and we'll define it as being a 2-variable K-map. And we'll label the 2-variable K-map. And then what we'll do is we'll number it. This will be 0, 0. This will be 0, 1. This will be 1, 0. And this will be 1, 1. And so we'll label it as 0, 1, 2, 3. And now what we'll do is we'll get a truth table. And we'll fill it out. And then we'll number the truth table. And it's clear elements in rows 0 and 1 are members of the onset. And so we'll put in the truth table, a mapping directly into the K-map. And now we can write out a canonical sum of products form. And clearly, we can manipulate it by factoring out B and saying that the whole thing is equal to A prime. And sure enough, if A is equal to 0, then the output must be a 1. So that's our simplification right there. And we did that with Boolean algebraic manipulation. But what we can also do is we can loop these two 1s and then write out this term here, A prime, and set it equal to F. So by using a graphic technique, we're able to exploit the idea that a variable can be factored out. And so this is the essence of the simplification of the K-map with a 2-variable approach. It's essentially a way to use graphics to do about Boolean algebraic minimization. And when we're done with it, we get a minimal sum of products. And a minimal sum of products is interesting because what it says is that instead of using 2 AND gates and an OR gate, we're able to substitute an inverter. And so now I can say F is equal to A prime, and I can implement it by taking A, passing it through an inverter, and calling that F. And this is much simpler than that. It's not only simpler, it's faster and cheaper. It takes up less space. So it's got, it's got advantages all over the place because it's a minimal form. So being able to arrive at a minimal form is a totally different skill set than being able to arrive at a canonical form. But it's an important skill set, and it's one that is covered in your reading. And I'll tell you where that's at. It's called two-level simplification, and it is starting on page 65. So what you want to do is you want to read pages 65 through 75. Oops. And that's your reading assignment. We'll cover that in some detail in our next exciting digital design class so that you guys will be able to handle homework number 4. Are there any questions? Does everybody have a book? Well, let me ask you this.
Yes.
Who doesn't have a book? At this point, everyone should have a book. Because there's a lot of reading in this course, and you got to try and keep up. Because as you can see, the course builds up on itself, and it, I'll cover stuff as often as you like in review, but we're going to keep going. Homework 1 to 2 to 3, and we're almost up to homework 4 here. So, what do we have due today? Today, I think we have a homework 3 due. Isn't that right?
I think it's homework 2.
Homework 2 is
Yeah,
due?
homework 2.
Yeah, homework.
Good, good. And were there any questions about homework 2 before I let you guys go? Everybody's all set? Nope, no questions?
Number 12.
Oh, number 12 of homework 2. Okay, we got time. Let's do that. I should have started off with that. Course content. Forgive me while I mutter to myself. Edit the test. Number 12. Going down to number 12. Oops. 11, 12. Okay, multiple choice. A, B prime equals A prime or B prime. What is that an example of? Well, what if I wrote it this way? What would that be an example of?
De Morgan's.
Yep, there it is. So the only thing that's different is the bar. All right, the bars, these are equivalent. So don't let that throw you. If you see the bar over the top, that's the same thing as the prime. Any other questions about homework 2? Well, all right. It's we got about a minute left. I don't think there's time to start any more problems. Unless you have any more questions, I think I'm going to let the class go. It's a beautiful day out, a little bit chilly. Stay safe and stay warm, and thank you very much for your attentions.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.